Assalamualaikum warahmatullahi wabarakatuh. Welcome back again to my lecture video. Okay, so today we are going to talk about a new topic, which is heat transfer through buildings. Okay, so in this chapter we are going to look at one part only, which is one dimensional. Okay, we are going to look one dimensional only. Okay, so before we proceed any further, let's look back, okay, at the types of heat transfer. Okay, so you should learn this in your thermodynamics class already. So we have three types of heat transfer, which is conduction, we have convection, convection, and also radiation. Okay, so conduction here means that transfer of heat between substance that are direct contact with each other. Okay, just like my hand, from this hand to this hand. Okay, the heat transfer through these two substances here. And then convection is transfer of thermal energy from high temperature to lower temperature via gas or liquid. Okay, so just like what ice. Okay, like ice can be melt easily when we put it outside. Okay, because a high temperature, okay, a heat from a high temperature region entering the ice, okay, entering the surface of the ice here, so means that the ice will absorb the heat, so that it will change the phase from solid to liquid. Okay, that one is convection. And radiation is transfer of heat through empty space by thermal radiation, and it is often called infrared radiation. This one radiation. Okay, so in this topic we are going to be focusing on two only, which is convection and also radiation. Okay, these two only. Okay, let's take a look at one dimensional steady state heat transfer through buildings. So let's look at this figure here. Okay, we will look at homogeneous wall first. So one dimensional means that we will look at this one only, one way only. One dimensional only, one way only. And this is a wall, okay, and this is a room. Okay, this is indoors and this is outdoors. Okay, so in this condition here, the temperature of the outdoor is higher than the temperature of the indoor. So if we look again at the convection is heat transfer from higher temperature region to a lower temperature region. Okay, so means that the heat from the outside will be transferred to the inside. Okay, which is why we have the direction of the heat here is like this. Yeah, heat convection, this one, convective heat here from the outside and then transferring to the inside. And also we have radiative heat also, okay, from the outside to the inside. Okay, and the total of heat, okay, there is transferring from outside to the inside is this one, Q in. Okay, so how to calculate this Q in? Q in here can be calculated using this one, convective heat from the outside plus radiation heat from the outside. Okay, this one is heat rate. Okay, heat rate. And then, or we can also use, okay, convective heat of the inside plus radiative heat of the inside. Okay, both same. Okay, this one plus this one is equals to this one plus this one. Okay, so we can use another equation, which is this one. Okay, Q in is equals to H multiplied with TO minus T wall. Okay, TO here is T outside, TW here is T wall. Okay, this one, T wall here, okay, of the outside. Okay, H here is what? H here is not specific enthalpy, but H here is actually surface heat transfer coefficient. Okay, not enthalpy, slightly different. Okay, and then for inside also we can use the inside properties to calculate Q in by using the surface heat transfer coefficient of the inside. Okay, inside surface heat transfer coefficient multiply with temperature difference of the wall minus this one. Okay, the temperature inside. Why this one is TW in the front, not at the back, just like this one. Okay, because this one here is higher than this one. Okay, the surface wall here, T wall here, is much higher than the temperature of the indoor here. So that's why we put it in front. Okay, so that we can get a positive value. Okay. So this surface heat transfer coefficient, we can calculate it using this equation. Okay, this one is for inside and this one is for outside. Okay, and this one also, convective also, we can use this one. Okay, and radiative we can calculate using this one. Okay, so there is another way we can calculate this Q in here. Okay, using this one, the properties of the wall here actually. Okay, so let's look at this one. Okay, so let's say we have this. Okay, this is our previous wall. Okay, and then this is our this one. Okay, thermal conductivity. Okay, this one here we can use. Okay, this inside here is the wall. Okay, so the wall here is built using a different substance. Okay, it can be bricks, it can be plywood, it can be glass also. Okay, so each materials has a different thermal conductivity. Okay, so we can use that thermal conductivity of the substance to calculate this one, Q in. Okay, how to calculate Q in here is using this equation. Okay, Q in equals to U multiplied with T outside minus T inside. So what is U here? U here is heat transfer coefficient. Okay, so how to calculate U? To calculate U, okay, is this one. Okay, 1 over U is equals to 1 over HI. So HI here is not enthalpy. HI here is surface heat transfer coefficient, okay, of the inside. Okay, and then plus with this one, 1 over H outside. Okay, and then plus with delta X over KW. Delta X is what? Delta X is the thickness of the materials. Okay, so let's say we have plywood. We have plywood as our wall. Okay, what is the thickness of the plywood? Okay, that one will be our delta X. Okay, and then over KW. So KW here is the thermal conductivity of the wall. Okay, let's say we use plywood. So we must divide it by the thermal conductivity of the plywood. Okay, this one. Okay, so we use this one here to calculate 1 over U. And then just change lah, U over 1, 1 over U, and then put it in this equation here, U multiply with the temperature difference. Then we can also get the value of this one, Q in here. Okay, and another way, okay, to calculate U here is by using this one. Okay, UO. So what is this UO here? Okay, UO here is actually this one. Let's say we have like a surface. Okay, we have a wall. Okay, so let's say we have a wall. Okay, let's draw a wall. Let's say we have a wall. Okay, so this wall here we have a door. Okay, let's say we have a door. Okay, this one door. Door. And then we also have a window. This one, window. Okay, window. Okay. So this, each substance here, okay, wall is created using maybe bricks. Okay. Door maybe what? Plywood. Okay. Window is maybe window supposed to be glass lah. Supposed to be a glass. Okay. So the total, this one UO here, okay, the total of heat transfer coefficient of this wall here that consists a window and door here is equals to this one. Okay. So U wall. So U wall is what? So U wall. So this one here will be, let's change the color lah. So U wall here will be 1 over Hi plus delta X, thickness of the wall, over K wall. So K wall here, let's say we use brick. So this one will be brick, and then plus with 1 over HO. Okay. So HI and HO for each part, window, door, and also wall, okay, we assume it to be equal. Okay. So this is when we want to calculate U wall. Okay. What about U door? Okay. U door. This one, U door here. So we calculate U door using same 1 over Hi plus delta X, the thickness of the door, over KW. So KW here is what? KW here, let's say our door is made of plywood. So this one will be the thermal conductivity of the plywood here. Okay, this one will be the thickness of the plywood. And then plus with 1 over H outside. Okay. So window also same. So window here. This one window here. So the KW here will be the KW of the window. Okay. So we add. So this one here. Okay. And then we multiply with the area of the wall. This one. Plus with this one U of the door here, this one, multiply with area of the door, and then plus with U window here, multiply with area of the window, and then we divide it with the total of this area here, this one, total of this area. Okay, so this is how we want to calculate UO when we have a different materials, okay, on the wall here. Okay, so this is how we calculate UO. Okay, so this is for homogeneous wall. What about non-homogeneous wall? Okay, non-homogeneous wall means that we have, for example, this one. Okay, we have a space inside our wall here. Okay, so the space, what does this space do? So sometimes we use this kind of bricks because we want to decrease the heat transfer. Because actually air is a very bad heat transfer material. Okay, it is not easily to transfer heat through the air. So that's why we have this one. Okay, the air inside the brick here. For example, if you know about thermos. Okay, the one that can keep our food or water warm. Okay, actually, thermos have two wall wall of the outside and also wall of the inside. So between these two walls here, there is a space here. Okay, the air space. So because they have this air space here, which is why the heat from the outside cannot enter easily to the inside. Or the heat from the inside of the food, the heat of the food cannot be transferred easily to the outside. So which is why it can keep your food or water warm or cold. Same like the window of the plane also. Aeroplane, if you look carefully, they have two windows. Okay, windows, space, and also windows. Okay, that one. Okay, so for this one here, because we cannot determine the U easily, which is why we use this one. Okay, single parameter here, which is thermal conductance. This one C here. Okay, and then we calculate C multiply with this one. Okay, the temperature of the wall outside and inside to calculate the heat. Okay, heat flux here. Okay. So as I mentioned earlier, different materials have a different thermal conductivity. So this is the table, okay, on how for you to determine the thermal conductivity of the materials here. Okay, let's say we have this one. Okay, bricks, okay, common bricks we have 0.77, and then glass we have 0.78, and then look at this one, insulating materials. For insulating materials, as you can see here, the number is much lower than the bricks and also the glass. So what does it mean? So it means that if we have a lower number here, so it means that it is much harder for the heat to be transferred from the outside to the inside. Okay. So insulating here, insulate means that we want to prevent a heat transfer, or we want to minimize the heat transfer. So that's why we use insulating materials. So when are we going to use these insulating materials? Of course, in Malaysia we have a very hot season, almost every day. Okay, and which is why to prevent the heat from the outside goes to the inside. So that's why we put insulating materials. Okay. So this one is quite expensive lah. But if you put it on your wall here, insulating materials here, you can decrease, okay, the heat transfer rate from the outside to the inside. Okay. So in the next lecture, we are going to look at one example on how to calculate the heat transfer rate from the outside to the inside. Okay. So see you again in the next video. Bye bye.